embedded condition, we had a webinar on this some months ago. So I went into the details of how to using embedded rebars. Okay, but the concept is that you first create an interaction, which is someone muted me. Okay, so the interaction is of type node to element. Okay, the master geometry, so the primary geometry should be the solid which embeds the other geometries. Okay, so I select basically the solid as a master, and then all the edges of these other geometries are as slave. Okay, so this is the basic procedure, very easy. After that, you will be able to see these symbols inside. This is basically saying that every node of the rebars is going to be attached to the nearest element. Okay, when you are in the geometry, this is not pretty clear, but when you mesh it, it will be much more clear. Okay, so basically every line here has a connection between to the node, to the element that embeds that rebar. Linsun, you said there are two voices overlapping on your side. Just a second. Just wait a second, sorry. This one is switched off. Now, can you hear me? Okay, sorry.
Yes, Massimo, yes.
Okay, so here we are. Can you still hear only one voice, or do you hear some noises?
Just one voice.
I think it should be fine now.
Just one voice, yeah.
Sorry, 1 second for the inconvenience. Okay, so we have the geometry, the interaction, and now once we have all of these, we can start with the physical properties as yesterday. Yesterday I was using the for concrete. Actually, for steel it is the same. So I will show you how. If we go in property here, and I switch off the embed because I don't need it here. Okay, you can see actually the extrusion for the rebars. For the stirrups and the rebars inside the solid. Okay, now the physical properties. Physical properties, we have the same aesthetic materials for the rebars. Okay, so we have the aesthetic material for the HD5, so the material model to be used in the rebars inside the wall, which are these ones. Then we have the HD12 for the longitudinal rebars. And then we have another material here, another aesthetic material, which is the one for the stirrups. Okay, so basically we have 1, 2, and 3 aesthetic materials. Then for each one of them, we need to create a fiber section and then a beam section property. Okay, because in the previous model we were using the smeared approach, so we just needed a uniaxial material, and then this material was converted into a shell layer. In this case, the approach is different because we are actually modeling the rebars as beams. Okay, so they are actually beam element physically modeled inside the solid element. So for each material, we need a fiber section. Now, to save time, I used a very coarse discretization, but basically you can create a circle. In this case, I created a circle with a diameter of 6, and then you can mesh it using this material model. Okay, and then I did the same for all the others. So fiber section for the HD6, the fiber section for the HD12, same kind of mesh, and the one for the rebars. Okay, this one instead has a diameter of 5. Okay, when you create a rebar, don't forget a fiber section. Sorry, don't forget to put the GJ, because many times people forget this one, and this is the source of singularity, because basically your rebar will be singular about the rotation, about its own axis. Okay, so once you have the fiber cross sections, you need to create a beam section property for each one of them. Okay, so this one is the section property for the HD6. I just need 3 integration points, the minimum amount for the Lobato scheme. Same thing for the HD12 and the R5. Okay, so once you have them, you can assign them to the lines that we created for the rebar. So for example, this one, if I click on select, you will see that they have been assigned, okay, to the rebars in the middle. Instead, if I select this one, they have been assigned to the longitudinal rebars for columns. And finally, select and show. These ones are the section properties for the stirrups. Okay, so this is fine. Once we have everything for the steel, we need to set up the 3-dimensional material model for concrete. Now, the material model we used yesterday was the plane stress user material. The problem is that that material model is a plane stress model, so it works only in 2D or in thin shells. Now, in this case, you need a full 3-dimensional material, and it should be also pretty fast, because in this kind of models, it will take a lot of time. So in this case, we are using the concrete DamageTC3D. Material properties are the same we have been seeing yesterday. So if you go on concrete here, you have the properties, but in this case, I'm using the real fracture energies, because those of you who know the DamageTC3D, there is the automatic regularization and the opportunity to input directly the fracture energies. Okay, so basically we have the homogeneous Poisson ratio. Then we have some properties for the tensile response, which is the FT and the GT. Okay, so tensile fracture energy. Then the compression. For compression, we have three items for the compression curve, which is the compressive elastic limit, then the compressive peak strength. Okay, so up to here, the response is elastic. Then you have a parabolic response up to this point. And then you have a parabolic softening followed by an exponential softening up to a residual plateau, in this case of 2.5. This one is the peak strength. Okay, and then you have the compressive fracture energies. Some few other parameters that can be left as the default. Okay, so there is not much going on here. This parameter here by default was 0.16, which was fine for masonry, but for concrete, it's better to use 0. Okay, so it gives the maximum dilatancy. And then I'm using the implex integration. Okay, now in the new version, you will find something new, because up to the previous version, you did not have these 3 items here, and also this 4th one. So you had only the opportunity to choose between implicit integration, which is the one that requires iteration, or the implex integration scheme, which is a mixed explicit-implicit integration. And you had the opportunity to do the automatic regularization. Now, those of you who have already used the implex algorithm, you know that it has an explicit part of the integration. Every time you use an explicit integration, it introduces some error. So now you have an opportunity to either use the implicit scheme, and in this case, you can choose between different tensors, because by default, we were using the tangent tensor. But the tangent tensor with the implicit algorithm can create some issues. So you have some opportunities to go with the tangent perturbation, which is a numerically calculated tangent matrix, or the secant matrix. The secant matrix is fine with the implicit algorithm because it is always positive definite. Okay, while the tangent matrix can have negative eigenvalues. So if you want, if you do not trust the inflex algorithm, you can go with the implicit. You can choose the secant matrix, but be prepared because you will need some more iterations. Otherwise, in this new version, you can choose the inflex. In this case, if you use inflex, don't care about the tangent matrix because the tangent matrix for the inflex will always be the secant one. So you can choose whatever you want. It will be overwritten. But you have some new parameters. You can tell OpenSees to automatically check the inflex error. What should be the maximum error in terms of percentage? So a value that goes from 0 to 1. And basically, if the material model has an error which is higher than the user-defined tolerance, he will try to reduce the time step to have a smaller error, okay? The problem is that maybe you don't want the time step to reduce to a minimum value, so you can put a minimum threshold. So for example, in this case, I'm saying that, well, in this case, I'm saying that I don't want any check of the error because in this case, I know how to deal with the index. But if you're not sure, you can say, okay, I want to check the error. I want my error to be 5% at most. If the error is larger than 5%, OpenSees is allowed to reduce the time step to a maximum of 0.2, the original time step, okay? So you can have a control also on the amount of reduction of the time step. Okay, but in this case, I'm not interested in this. I will give a webinar on this topic later. A simple example of what we do, this one.
The constitutive model, how you
I
correct
can show
it
it later on. Okay, so first I will go with the webinar, and then if I have time, otherwise we can.
Absolutely.
It's a lot of time actually to explain all this stuff. Okay, so we will go with the standard inflex, and then if I have time, or probably we can set up a webinar on this topic. Okay, so this is fine. This is everything for the material model. Let's press OK. And well, the top beam and the bottom beam in this case are still considered elastic. Okay, so I just use a three-dimensional material, elastic isotropic, for both bottom and top beams. Then we have the steel plates here at the two sides. Okay, as yesterday, but now they are not shell, they are actually solid element. And now there is a slip condition. Then I will explain you later on what it is. Okay, so now what I will do, because in this model I made two stuff. So basically the default embed condition and the embed with the bar slip. So don't care about this. I will show you this later on. Okay. And then we have the definite elements. We need a solid element for the hexahedral mesh here. In this case, it is the Rebars brick, and the displacement beam column for the rebars. Okay, the displacement beam column is fine. We don't need the force beam column because the rebars have a very fine mesh. Okay? So we don't need to take advantage of the force-based formulation. Now, boundary conditions. What do we have here? So we have a fixity of the base. Okay. So the entire fix here at the base, but it is also fixed on top. You can see it from the test setup. Of course, in this case, I'm not using a shell anymore, so it is just sufficient to use 3D and displacement. Then we have the same weight everywhere, basically, because now we don't have to deal with the thickness of the shell as we did yesterday. Okay, so yesterday we created basically 3 different self-weight. Okay, one was for the pressure in the mid face because it has a certain thickness. Then there was another pressure for the top and bottom beams because they have another different thickness. And then there was a line load for the columns. Now it's much easier because all of them are solids, so we can just put the self-weight of concrete. Okay, I'm using Newton and millimeters, so the self-weight is 2.5 to the power of -5. So this one is the only vertical load available in the model. Then push load. The push load is, as yesterday, an imposed displacement on the central node here, okay? And it will basically push monotonically the wall in the minus x direction. Yesterday, one of the participants, Ninsun, asked me, how do I deal with a cyclic loading? Because in this kind of test, I can push it here, but cannot pull it from here because the test is made in such a way that when the actuator here is pulling, actually the compression force will be applied on the other side. It will be a little bit complicated, but I prepared an example for that. But first, we will start with the monotonic approach. Okay, so a simple imposed displacement there. And then I have two kinds of embedded. Now we use actually the first one. So I edit this one. Actually, I don't want to use it. So it is fine, but I want to use the default embed. And then I will show you what is the new embedded, okay? Okay, so in this example, don't look at this last condition, it is not used. What I'm using is this condition here, which is called ASDEA embedded node element. It's a penalty-based condition that basically attaches every slave node to the nearest, in this case, solid element, okay? In such a way that if a node is on the surface or inside a volume, it will move accordingly, okay? So as a weighted average of the displacement of the bounding domain. Basically, you have few parameters. A stiffness parameter, here you have a description. It should be more or less the stiffness of the concrete with some order of magnitudes more, okay? So in this case, the concrete was 25,000. And here I added, I think, yeah, 2 order of magnitude. Since the elements inside are beams, I also want to constrain rotation of the beam to the rigid body rotation of the displacement component of the solid. And I don't need to constrain the pressure because I'm not doing, I'm not using UP elements as in solid structure interaction, okay? So this is the default when you want to embed rebars with 6 degrees of freedom inside a solid. But this one, actually, this was the original formulation that we had, that you have also in version 3.0, that simulates basically a perfect bond, okay? So the node will always be inside the element. Someone yesterday asked me if it is possible to there is a question here on the forum by Ibrahim. I asked regarding pinching effect in case of cyclic loading, but what are you referring to? Are you referring to, you asked this yesterday? Because I don't remember about this question. Or can you explain pinching of what as a specific constitutive model of the overall pinching of the shear wall? Okay, so, okay, can the concrete model consider this? Well, it's not the concrete itself. I mean, pinching effect that you see in material models, such as, for example, the pinching 4 in OpenSees, they are phenomenological models. Actually, the pinching will be automatically visible as a combination of the crack opening in shear in concrete with the plasticity of the rebars, okay? So you cannot actually specify how you call it, the pinching directly inside the constitutive model, okay? The pinching effect is an overall effect, okay? So it will be visible in the final curve, okay? But not inside the concrete model, because if you look at the concrete model itself, it does not have pinching in that sense, okay?
Massimo, can I ask you a question?
Well, I will show you also how this material behaves. Okay, so if I close this one and I go to the concrete, okay, so if you want to understand how the concrete works, you can just play with it a little bit. So I will show you now how it will look like inside OpenSees. So OpenSees basically will take this yeah, Joel, please go ahead.
Now, please finish what you were saying.
That's the problem.
Finish what you were saying.
Just a second. I cannot hear anything from here.
Can you hear me? Can you hear me now? Hello? Hello?
Hold on a second. Non sento l'audio del tuo. Parlo io, non sento più. Just a second, sorry. Joel, just a second. I cannot hear anyone here speaking. Un attimo che il pallone come scappa. Okay, can you hear me now?
Yes, can you hear me?
Yeah, I can hear you.
Oh, okay. I'm very sorry for that. I didn't mean to interrupt you.
No, actually, it's not a problem. Yeah, go on.
I wanted to ask you a question about the embedment.
Yeah.
You mentioned that when the rebar is embedded in the concrete, in the solid, the node of the rebar follow the displacement of the solid that is obtained as a weighted average of the nodal displacement, right?
Exactly.
So I understand this, but then you added that you add another constraint about the rotation.
Exactly.
Is it redundant or partially redundant? Can you comment on that?
Yeah, I can show you. Actually, it is on the OpenSees documentation. You can see the equation actually. So if I go on OpenSees GitHub documentation. Command manual, modeling. Then we have element commands and ASDEA embedded node element. Okay, so basically, if you look at the equation for the two-dimensional case, okay, so basically what I do is that I have a constraint node, which in this case is the node from the rebar. Okay, it falls inside an element. In this case, a triangular element, for example, and we have node restraint 1, node restraint 2, node restraint 3. So the x displacement of this node at these local coordinates will be a weighted average, where the weights are basically the shape functions evaluated at this point, of the same DOF of all the nodes. Then I do the same for the y displacement. Then if this node, if the constraint node has a rotational DOF, as in this case, the rotational DOF is not available in the solid, okay? As a deformational rotation, because I'm not using a Cosserat continuum like in a beam. But what I have is that I can get the rotation at this point as the rigid body rotation of the element. The rigid body rotation is basically the skew symmetric part of the displacement gradient, okay? So basically I have the displacement gradient here, and this operation here is the skew symmetric part, okay? So basically I'm saying that I take the rigid body rotation and I take that scalar at this point, and I enforce the rotation of this node to be equal to the rigid body rotation of the element. Okay, it's more or less as the
yeah. Thank you very much. It's very clear. Yeah, very clear. Thank you.
Okay. Okay, I don't know if there was someone else trying to ask a question, because before I couldn't hear any question. Okay, so I think it was only Professor Conte. Okay, let's go on. So for example, if you want to see how this material model behaves inside OpenSees, you can use the material tester. But of course, you have to keep in mind that now OpenSees will divide the tensile fracture energy by the element length. So for example, in this case, the element size will be 200. So this one will be actually something like 0.007, and this one will be 0.17 more or less, okay? So in tension, this will be the behavior. Okay, so this is the tensile response. In compression, it will be, you see this one is the peak strength, so it will be a parabola up to this point, linear up to 20, then up to 25. If you push it more, you will see the softening. Okay, softening up to a residual plateau, which in this case is 2.5. So if I push it even more, you will see the residual plateau. Okay, so this is how it looks like in OpenSees. Then based on these two parameters, you can define how much, what is the amount of plasticity. Okay, in the model I showed yesterday, it was 0 and 0, because actually the model by Professor Liu Xingzhen is only a damage model. So if I do a cyclic test now with 0, 0, you will see something like this. Okay, but now here we wanted to include some plasticity, like 0.6, 0.6, both in tension and compression, so that you can model the plastic deformation in concrete. So this one is what happens in uniaxial test. If you want to see how this material model behaves in shear, you can go here, you can say, okay, I want to test the shear part, and the other components are stress controlled, okay? So now in this case, it is pure shear. I will apply shear and 0 stress everywhere else. So I can go here and see how it behaves. Now in this case, I want to apply a cyclic and symmetric loading. Okay, up to this point should be fine. Okay, so this is the shear behavior. Okay, so you have some plasticity, but it goes, as far as it goes here, it loses some plasticity here. So basically you have strength degradation. If you want to see how it behaves, so basically here the strength is pretty much equal to the tensile strength, which is actually equal to the tensile strength here, because I'm using the Rankine criterion. If you want to see how it behaves in compression, now we are testing the shear 1, 2. So you can apply some pre-compression in the 1 and 2 direction to see how it behaves. Okay, so this is the sort of pinching effect you can see here, and you can see an increased shear strength. Okay, so this is perfectly normal. If you want to see more plasticity, for example, you can expand the plasticity of compression up to 1, and then you will see, okay, this residual plateau. You can play with it based on your the material model that you're trying to model, but values like this for concrete are more than enough. Because actually the plasticity part is then given by the rebars. Okay, so now I press cancel because I want to come back to the original values. Okay, let me double check them. Okay, perfect. So we can go on. So as I told you, this is the material model. We have everything here. We have this standard embedment. Okay, so now the rebars are considered perfectly bonded with the concrete. And we will see actually that in this model, we may need strain penetration. So once we are done with it, as usual, we create a recorder. Now, in this case, I want to record just the displacement, stress, strain, and damage. I don't need anything else. Just to speed up the analysis, I want to record every 10 steps. Okay. Then you have boundary condition. Now, in this first test, I'm just using the fixity at the base and only one embed. Okay. I defined two of them because I want to show you the difference between the standard embedding and the embedding plus bar sleeve. But now I'm using the standard one. Okay. So perfect adherence. Then, as usual, gravity loads. Then the gravity analysis. The only difference that you will see here that I'm using parallel computing now, because now this model will be slightly more expensive. Dudchenko, hi Dudchenko, how are you? Isn't the latency still depends on the stress condition before yielding and not the material parameter? Probably we have been talking about this one. As I told you, this is a simplified plasticity model, so that you cannot actually specify directly the latency parameter, but the number that you put here, and it is also explained in my paper about micromodeling, the number that you have here basically governs the latency if you are under shear stresses. Okay, so a value of 1 is basically the minimum amount of the latency that this model can show. A value of 0 shows the maximum the latency. The only problem is that you cannot choose a real value of the latency. Now, this is not a major problem because actually, even if you have models where you can specify a real value of the latency, in real life, the latency is not constant anyway. I mean, you can have some latency at the beginning, but when the material starts to damage, the latency goes down. So it's a very aleatory variable, okay? But this as before. So in this case, you can, the lower this value is from 0 to 1, the larger is the latency. Okay, so let's go here. I can close it. Gravity analysis. Then we have the push load. In this case, I'm using the linear time series, but after I will show you how to do the cyclic one. Then I have a monitor as before, and the displacement controlled analysis, which is actually, as I told you, a load controlled analysis because I'm applying an imposed displacement. Okay. So also here, the only thing that you have to do is to use a parallel number and a solver which supports parallel computing, which in this case is MUMPS. Okay, so I can run this. I think it will take a few minutes. So let's see how it goes. Let's run it. I'm using, I think, 4 processors. I will show you the mesh now. So this one is the mesh. It is a quite coarse mesh because now I don't have time to run in real time a finer mesh. But this is sufficient to obtain some decent result now. Yeah, I'm using only 4 processors. So 15% in 20 seconds is pretty good. So once again, in this case, we are using perfect bond. Okay, so you will see some improvement later on with the bars and stem penetration stuff. Okay, so let's wait for this one to finish. You can see using the Implex tool how the convergence is much better now. Because yesterday with the standard nonlinear model, it was taking a lot of iteration to converge. But the advantage of the Implex is that it makes the analysis much more convergent. Okay, so it's almost done, 93%. Okay, so let's see what it looks like. Solid embed. Yeah, this one is the one that I ran before, then I changed the name. Oh no, I forgot to change the name. So this one is the one that I'm running now. Yes. Yes, let me just double check the shell embed. Yeah, this one is the one I run now. This one was the test I was doing before. Yeah, I renamed it, yes. Because I actually was using the same, I built the solid model from the shell model that I used yesterday, and I forgot to change the name of the recorder, but it is fine. Let's switch off this. And I want to move to material strain, principal max. Okay. So now, of course, the mesh is very coarse, but this is what you can obtain. So basically, it starts with the initial fracture here at the bottom, then some other flexural crack, and then you have a change from bending crack to a diagonal crack. Now, if you want to obtain better results, you can go, well, up to here where you have basically the joining of the diagonal crack to the bottom, and you have the crashing here at the side, okay? But now what you can see here is that basically the column here, which was the same thing that was happening in the previous model where the beam was modeled as a beam element, basically everything is damaged. You don't see cracks here. So probably this kind of behavior was due to the strain penetration, which is not modeled in this case, especially here. The rebars which are embedded in the damaging model, they actually are still completely attached to the concrete. Well, actually the concrete there is gone, okay? So probably using the standard embed is fine, but not so much in this kind of cases, okay? So now we have a new tool in the new STKO, which is this one, which is the embed and slip. Well, actually it's pretty similar to the other. You can see that you still have a penalty parameter, okay? Same meaning as before. You have the same options. Of course, you don't have the option of constraining the rotation and constraining the pressure. Why? Because actually we can use this constraint only between a beam and a solid, okay? Because it is made exactly for rebars, while the other one is a pretty generic constraint. So by default, the rotation will always be constrained. And by default, the pressure DOF is not constrained because it is not supposed to be used between soil elements like UP elements, okay? So you only have the penalty parameter and the bar slip material, which is defined here. It should be uniaxial material given as stress versus displacement. So the bond stress versus the displacement slip. And then, of course, I need the rebar diameter, because basically what it is doing is something like this. Let me do an annotation. So while before basically I had an element, so for example, before we had an element and then a node, okay? So this node was constrained to move exactly as the retained nodes of the element. Now what I'm doing with the bar, with the embed, that I'm creating a duplicate of this node. Sorry, can you mute, please? Okay. So what I'm doing with the
Huh? What is it? Is all?
Yeah, I can hear you, Massimo. I don't know if it's only my problem.
Yeah, yours is.
Huh.
Guido, come on. Come on. We need to mute ourselves.
No, I still can hear you.
Pronto, visto? No, non lo so, però non sono io.
Vorrei così io.
Okay, sorry everyone. Can you hear me now?
Yes, yes, now it's fine.
Okay, sorry, I think I've been talking without the microphone. Okay, so I was telling that this boundary condition is basically similar to the previous embedding condition, but instead of embedding directly the beam node to the element, what I'm doing is that I'm creating a duplicate node. Okay, so this one is the node coming from the beam. Actually, I'm creating a duplicate of this node at the same position. This auxiliary node will be completely bonded to the element, while this other is equal DOF to the secondary node in all the direction. except from the axial direction. In the axial direction, I apply a custom constitutive model that can be used to simulate the bond slip. Okay. Okay, so I will create actually a webinar on this new material model, but just to explain you how it works. Okay, so you can, when you want to simulate the embed plus the bar slip, you can simply switch to this new constraint element. But of course, previously you have to define a bar slip model. Now, in this case, the bar slip is a simple aesthetic model. Well, I didn't have time to find some real equation. I just put some numbers here. So I put an initial shear strength, which is equal to the shear strength of concrete for a certain displacement, and then it goes up to 6 megapascals at a certain displacement, and then goes down to the ultimate displacement of this one. So if you see the test here, it starts with a bond of 3.0, then it has an hardening up to 6, and then it goes down in softening down to I think 1.1, an ultimate strength of 1. Okay, so you can play with it. You can compute it based on the type of rebars that is available in this test. This is just an example to show you the effect of including the bar slip and how it looks like in the results. Okay, so this is my bar slip. I put it here, and then I go to the boundary condition, and instead of using the standard embed, I use the embed and slip. Okay. Now we can try to run the analysis and see how it looks like. Of course, now the computational time will be slightly larger because now we have some duplicate nodes, but not that much. And now we will see the difference in terms of global response, and then I will show you how you can visualize the bond response or the bond slip response at the Gauss point level of each rebar. So you can see here that now you have a much smoother transition, while before there was a steeper descent here. Okay, so let's see. Okay, 40%, we're almost done. Then here at the end, I think we will see some convergence issue because I'm using a softening model here, the bar slip, which of course does not have the implex algorithm. So you will see that when you have softening without implex, it will take a little bit of time, but ultimately it will converge. Okay, now I'm starting to have some convergence issue here because I think it was the point where the bar slip was going into softening. I think it will take a couple of minutes to finish. It just has to pass, yeah, past this point here. As you can see, when using the Implex algorithm, you have a lot of advantages. As soon as you put a standard material models with softening, but without any special algorithm, even these small jumps here will create a lot of issues. And the problem is that the analysis time will grow a lot because you move from 3 to 4 iteration up to 60 iterations, so that the computational time will be much more. So actually, step by step, we will try to implement the Implex algorithm also on other material models. So now it is running. Just let me see. Okay, yes, it got the softening. Okay, now it is accelerating because now it passed the softening point. Now it is accelerating a little bit. Then probably we'll find another softening here. So I think I will try to load the output because I think it is enough to visualize what's going on. So I save this and I reload it. Now here, if you remember, here you have all these column, which is completely damaged. I reload it. Now you can see that it's much different here because now there is not a complete damaged columns. Now you can see actually the cracks that are alternating. Okay, so you have a crack here, then a virgin column here, then other cracks and so on. This is due also to the rebar, to the bar slip that we introduced now. While this is going, I will show you how to visualize the rebar. Okay, so it is not necessary we keep waiting, so I can stop it. Okay, I reload everything. Okay, up to here. Okay, so I want to show you what actually the bar slip is doing. So this one is a solid response of the entire domain. If I want to see what's going on inside, I can create a new plot. I go on Gauss point plot, because in the Gauss point, I can visualize what's going on at the Gauss points of the solid. In this case, it is by default, it is using the damage. Okay, so you can see the damage development here inside the volume.
I'm sorry, I again don't hear you.
Okay, can you hear me now?
Yeah, now it's fine.
Okay, for some reason it unmuted randomly. I don't know, someone is trying to unmute me. Okay, so as I said, you move to the Gauss plot and then you look at material strain, but not the one for volumes, the one for lines. As you can see, you have 6 dots, but these 6 dots are actually the 6 dots of the spring that I put between the beam and the solid element, okay? Now pay attention that this spring is actually a force displacement counterpart of the stress displacement curve that you gave. So basically what it is doing behind the scenes, I will show you. But if you use the embedded element with the embedded node with the bar sleep, what I'm doing, if you go in analysis steps, just to have an idea of what this automation is doing, is this basically. Okay, so for every node of the beam element, I create a duplicate node. Okay, then I create the uniaxial material that you gave. Okay, is already available in materials, which is this one. So here you have the uniaxial material hysteretic for the pinching, which is the number 42. But now for each node, I'm creating a copy of, a wrapper, which is called multiplier material, that basically takes the output of the original material, which is this one, and multiplies it by a value. This value is actually the tributary area of that node. In this case, the tributary area is nothing but, so imagine you have, this one is the element. Then here you have a beam, here you have a node, and here you have the other nodes of the beams. I duplicate this node. This node will be embedded to the solid geometry. Then I take this node, I create a link here, and in this link I put a uniaxial material in the axial direction. Now this uniaxial material is given as a stress versus displacement. I want to convert it into a force versus displacement. That's why I ask you for the diameter, okay? So that from the diameter I can compute the circumference. And from the mesh, I can get the tributary length on this side and tributary length on this side, okay? So with the circumference and the tributary length, I obtain the tributary area. So I take your stress and multiply it by the tributary area, and I convert this one into a lumped force displacement item, okay? So that's why here you see a duplicate node. This duplicate node will be embedded, okay? And then between the two, I create a zero length element, which has a very stiff material in all the direction. But in this direction here, it will have a multiplier, okay? And this multiplier here is actually the tributary area. So this is just for who is interested to understand how it works. But the point is that if you go on Gauss plot, you go here, you can see actually what's going on in terms of bar slip. Right? So I can increase this one. Okay. So what you can see is that you have major stresses here. So actually, this is actually modeling strain penetration. And this also happens around the crack, okay? Which is basically what was not happening before. Before, we had a lot of stresses around the crack because the rebar was still embedded into the damaging concrete. In this case, the rebar can actually slip, okay? So actually, if you try to look at one of them, you will see actually how it moves relatively to the original node, okay? But actually here you have a zero length element. It's easy to visualize with a Gauss plot. You increase a little bit the particles and you can see these values here. Okay, so if I try to do an animation, you will see how they start here with a very small value. And then when the crack forms, you can see the bar slip that actually follows the crack. Okay. So basically the rebars are capable of slipping from their initial position where the concrete is damaging.
Massimo,
okay, so
I have a question.
Yeah, sure.
I have a question. Can you plot the, I think it's typically called stress slip, you know, shear stress versus slip
yeah.
plots, you know, for seeing at the interface of the rebar and the concrete.
Yeah.
See the cycle and the degradation. Of course,
yeah,
here it's monotonic, but
yeah, in this case it's monotonic. Actually, the stress versus displacement is this one, the one that I assigned. Okay. Now, what you will see there will be this one multiplied by the area. So you will see the force versus slip. Okay. So keep in mind here you have 6, but you have tributary areas of the order of, let me go back to the analysis step, of the order of 1,000 more or less. Okay. So that's why you will see a value, an ultimate value of about 4,000. Okay, so if I go back here,
You need the
But
golf
Massimo
ball.
was saying that would be also interesting to see the shear slip also, just for the users. I agree. Like in the app.
Shear
just the
stress,
shear
shear
slip.
slip. Yeah.
I think let me double check something, because probably it is already possible. Just let me double check, because if the multiplier material allows me to ask the stress in the original material, I can get the shear. So let me just multiplier C++. If we are lucky, no, it's called multiplier.
In other words, the same material model that you put for the interface, like you put a shear stress, shear slip there, and then you would want to see at a certain location of a rebar, where are you on that shear stress, shear slip model?
Yeah, exactly. I mean, now you can directly do it. For example, if I do this one, I can do it. But what I obtain, because of the results that I asked material dot strain, what I can see now is that if I look at material strain on the lines, first component, because the other are stiff, okay? So stress on lines, first component, next. What I will obtain will be the force versus slip, okay? So this one is what I'm obtaining. So I reached the initial value, then here, due to the damage, I have a small snapback, and then I kept on going. Now, in this case, for example, I reached the hardening part, but I did not reach yet the ultimate strength, which is about here. Now, actually, if you want to see what is the stress, you need to know what is the tributary area, but it's not strictly necessary, because actually you can visualize what is the slip, which is 0.8. So you can actually go on the material model, do a test up to 0.8, and you can see where we are. Basically, we are here at a stress of 4.5, okay? But as I told you, if we are lucky, the multiplier material has a method called set response. I just want to see if there is, no, unfortunately it is not. There is not a set response method, because actually what I can do is to create a modification in OpenSees to ask for the original material response. That in this case, it will give me the stress, not the stress multiplied by the tributary area. But for the moment, what you can do basically is to get the force. What is it? The force versus displacement. And then, since you don't know the tributary area everywhere, but what you know is that this is the slip that you have. And from the slip, you can go back to the initial equation and get what is the slip, what is the bond stress at that value of slip, okay? Okay, so basically this is the effect of the slip. And then one last thing I want to show you today is what Lin Sun was asking me yesterday. How do we apply cyclic loading? Because actually this model is very sensitive, because actually this is a shear wall subject to a cantilever kind of boundary condition. And since it is a squat wall, but actually it's a square wall, it is something in between the bending failure and the shear failure. So it is very sensitive to the location of the applied load. Now, if you want to do the cycles and you look at the paper that I applied here, that I will upload on the reference folder, which is this one. Where is it? Reference. On the reduced part here, I think I also put the here, this one. Okay, so basically here on the right-hand side, they applied both positive and negative load. Now, a positive load is actually pushing, but the negative load, if you apply in the finite element model, if you apply it directly here, you actually will be pulling the wall, which is not correct. Actually, what you want to do is to pull here this plate, but it will apply pressure, a positive pressure on the other side. Now, how can you do this one in OpenSees? Well, one solution would be to do a a displacement control analysis, actually to do several displacement control analysis, one for each cycle. Okay, so in the first cycle, you apply a load on one side, then you remove that load and you apply the load on the other side, but it is actually a mess because you have to create several displacement control analysis here. And every time you have to put a load and remove a load, so it's not so easy. So another solution is very fast is to use contact elements. So you can use actually a physically based approach. So what they do here is to basically push and pull this side. Then this side is rigidly linked to the other side, so that when I pull this one, here I will have separation, so no traction because there is no contact when it is separating. But through the contact, it will apply a push curve on this side, okay? So let's try to see how it can be done. I save this, and then I open the other model, which is here, solid embed cyclic. Now, if you open this one, it's basically the same model as before. I didn't change anything. The only thing that I did is, as you can see here, you have two other geometries, which are actually two vertices, one on one side and one on the other, okay? Let me go back to geometry. If I switch it off, you can see that now I have the point right, which is this one, and the point left, which is on the other side, okay? So these 2 points are actually located at the same location of the central point where I was applying the load before, okay? So once again, I hide it. Then I created an interaction for the rigid link. Now, what I want to do actually is to move these two nodes upwards so you can see what's going on actually. So I select them and I move them like, let's say 300. Okay, and then I switch everything on so you can see what's going on here. So I created two auxiliary nodes at the same location, then I will move them back. Then I created an interaction here for a rigid link, okay, in such a way that they are rigidly linked together, but they can rotate as a rigid body, okay? So it is very important that we use an interaction for a rigid link. This one is a simple node-to-node link. Then I created another node-to-node link for the contact. This node-to-node link is going from left to right, okay? So basically this link is this one. It connects this master to this slave, and then this master to this slave, okay? Perfect. So once I will move them backward, you will see just that they collapse. It's basically a spring on the two sides. It is very important that they go from left to right, because then I assign this local axis here, which is this one, is a local axis where the local z-axis is aligned in the positive x direction, okay? Which is the same direction in which I created this link here. Why? Because this one will be the contact normal, and the contact normal should always be pointing from the master to the slave, okay? So this one is very important. I move back actually we'll move back later on. So you have two extra nodes, one local axis, two interaction. One is the rigid link, two are the springs for contact. Then you have, of course, the rigid link, which is simply this one. Then I have, since the contact does not fix the rotational doves, okay, so just to avoid a rigid body rotation of this one along its own axis, I fix it in the out of plane direction. Okay, so I fix the z direction, which is the out of plane direction in this case, and I fix the two rotation along its own axis in the out of plane, basically, because I'm not interested in that. But I allow the rigid body rotation about the global z-axis, okay, which is this one. This one, don't look at this one. This one is a local axis. This one is the global axis, okay? Perfect. And then we have the rigid link. What else? We have the contact element, okay? The contact element is assigned to these two links, and basically it is a hard contact with some hard contact in the normal direction with some friction. So if I select this, you can see that the contact element is assigned to this two links, and basically it is a hard contact with some hard contact in the normal direction with some friction. So if I select this, you can see that the contact element is assigned to this two links, and basically it is a hard contact with some hard contact in the normal direction with some friction. So if I select this, you will see that it is assigned to these two springs, okay? Okay, so with this one, basically we are done. So what will happen is that, oh, and if, last note is that the push load, of course, is not applied to the old node here, but it is applied on this one, which basically represents no, it's not this one, it's the reduced, represent this point basically, okay? And the other point, this one, and the rigid link represent these connectors, okay? So basically, when I will be pushing, the contact here will be active, and here it will be inactive. When I will pull it, here it will be in separation, so no contact. Here will be in compression, so contact will be transferred to the other side. Okay, so we run it. Oh, of course, now I change the push load to a -1 instead of -30, because now I'm using the cyclic load where the absolute value is already the total displacement, okay? So the other change is simply that the push load now has another cyclic, another time series, which is the cyclic one.
Massimo, a question.
Yeah.
The normal spring stiffness that you put was, I think, very, very large. So you will have a negligible relative displacement between the steel plate and
Exactly.
the end of the concrete beam. You will not introduce some artificial pinching, right? Due to that, it will be negligible.
No, it will be negligible because actually one to the power of 10 is much larger than the typical stiffness that I have here. So once again, for example, my typical stiffness is this one times the length of the element. Now I'm using a length of 100, and once again the stiffness, the order of magnitude will be around log 10 of this value.
Yeah.
And around to the 0 number. Okay, so it is 6. I'm adding 4 order of magnitudes to the typical stiffness, so it's very negligible. Okay, so yes. Okay, so this is fine. Cancel, and we can run an analysis. Well, of course, one thing that you have to keep in mind is that now you have to increase a lot the number of time steps, because before I was using, I think, 500 steps to do a single monotonic load. Here I have several cycles. Of course, I need more numbers. So we don't have time to run the entire analysis. I will just run, or actually, I already have it. So if you run it, you can visualize the entire stuff, and you can play with you can also play with what is it? The properties for the plasticity in concrete. So these two numbers. But what I want to show you now is that after you load it for a few cycles, I want to show you how to visualize the contact force. I think here I made a couple of cycles. Yeah, then I didn't have time to show everything, but I don't need this one. I want to show the Gauss point. Yes. If I show the Gauss point, and well, in this case, I also ask for local force, and the local force is giving me for the contact springs is giving me 3 components: the normal force component and the 2 tangential forces, because it is a frictional contact. Okay, so now it is a Gauss point, which is here. Okay, now we'll make it a little bit larger, and I will increase a little bit the deformation, so you will see also the separation. And let's say 10. Well, I can put even more. Okay, so now you will see that, let's start from the beginning. Okay, so the very beginning is very low. It's just due to the Poisson effect on both sides. Okay, because there is a little bit of Poisson effect. But then when I start, okay, now it is pushing here. So here you have 0, because as you can see, there is a separation. And I also have to show you the nodes. Okay, so these nodes represent the other parts of the plate. It is in separation, so the normal force is actually 0. In this case, instead, there is contact, okay? So they are in the same location, but the normal force is much higher, is much larger, okay? And then let's see how it goes. So you apply force on one side, then when you unload it, it goes to 0, change direction, it goes on the other side, okay? So it's a very simple way of applying a force on one side or on the other, while keeping the single point constraint only on one point, okay? The other way, if you don't want to introduce contact, you don't want to introduce other stuff here, you can simply try to implement a displacement control with swapping the loading point, but it's going to be a mess, okay? So this is one thing that you can do. Just an idea to show you how you can use contact for this kind of simulations, okay? So I think that it's all for today's webinar. We have some minutes for questions. So if you have some questions, please go ahead. Oh, and by the way, by tomorrow I will upload all these files. I will apply all these files, and also tomorrow I will release version 3.1 of STKO, where you can find all these new tools, okay? So one question for Lynn. There are many ways to model a wall, like embedded solid element, embedded shell element, smear shell element. Could you explain briefly different ways, pros and cons? Well, I mean, this is always, whenever you approach different modeling at different levels of details, whenever you add details, so that you increase complexity of the model. If you know how to do it well, you have some advantages, because you can capture something that is not available in the other models. So for example, here you can introduce bar slip, while it was not possible on the other in the other approach of the smearing, as we did yesterday. Something else that is available in this model is that since the rebars are made of beam elements, you can actually model directly the dowel effect, while it was not possible in the smear layer approach. But the disadvantages, of course, are the expensiveness of the computational cost. And another problem is that the more details you put inside your model, the more attention you have to pay to the boundary conditions. So there are advantages and disadvantages with every stuff. So typically I would use this kind of approaches when you really want to study the details of an experimental test. But of course, you cannot think of building an entire structural model with several shear walls entire with solid elements. So it depends. So it can be useful also to create this model to understand what are the physics that are interesting or not, what is important to model or not. Okay. And in the other two webinars, actually in August, I will show you some simplified models. So how to use like the multiple vertical line elements that can be very useful when you want to model the entire buildings and you don't want to go into the details of a micro model. So it really depends on the kind of analysis that you have to do. Okay. Is there any other question? Something that is not clear?
And Massimo,
Yeah.
along the same line, so you can also, as we know, right, embed rebars into a shell element.
Yeah.
Instead of solid element, right? So it would be very similar to what you did here.
Exactly. It's super similar. It's exactly the same thing. The only thing that you cannot do with the shell element is to embed the stirrups, okay? But actually it's not so important. In this example, it was not important at all. So in a shell element, what you would do is to simply embed the longitudinal rebars as a single equivalent rebar in the middle, okay? If you, in this case, I tried to put all the details that I could. Well, of course, you can make it even better. So, for example, in this case, I put the bar sleeve, but I didn't have time to put also the the hooks here. So probably it is when you model bar slip, it is also important to the anchorage that you have here. So it really depends on the amount of details that you need to analyze. Okay, but yes, you can use the embedded rebars also with shells.
Here, for example, because you modeled the column on the side, right, with solid element, if the boundary or the column of the wall is in compression, so you will mobilize the confinement from the stirrups.
Exactly.
And in a way increase your compressive strength. Have you ever tried on an example like this to plot, you know, like let's say the axial stress strain in compression and see that this increase of compressive strength is visible in the numerical result? It's not negligible.
Actually, it is visible. In this example, it was not necessary, actually, because in this example, they did a test without any added load. So here, the increase of strength that you will see is very small. But actually, yes, the constitutive model can show you an increase. So for example, if I go directly on the constitutive model here, and I try to do a compressive test, like a monotonic test, and I push it up to the, well, just slightly above the peak, like this one, oops, like this one. Okay, so this one is the value that I assign as a peak strength in uniaxial compression. Now, let's say I want to apply a transversal compression of, I don't know, 2 megapascals. Okay, you can see I'm already at 35 instead of 25. I can keep on increasing.
I see. Yeah.
So actually, it is already visible from here. Now, in that example, it will not be visible because actually, in this example, it was explicitly said that they did not put any vertical load, just a self weight, because any added load would have increased the strength of this panel. So they decided to keep the shear strength as small as possible. But yes, using a three-dimensional model gives you also the advantages of modeling the confinement.
Yeah, thank you.
Yeah, you're welcome. Is there any other question? Okay, if not, thank you everyone for joining this webinar. Just a reminder, so tomorrow I will share the first two, the materials for the first two parts, so the yesterday's webinar and today's webinar. You will find the reference folder and these three folders, shell with the smeared approach, and then the two models that we did today. And don't forget, in August, I think well, we will send you an email as a reminder, but I think it was 24, 27 of August. We instead will try to use some other approaches, like the multiple vertical align element, which can be very useful if you want to speed up your analysis instead of doing the micro model approach. For example, if you want to model shear walls in a real three-dimensional building. And finally, we will use the cyclic truss model from Professor Restrepo. Okay. And finally, in September, we will have the concluding webinar with question and answers and a roundtable. Okay. So thank you very much for joining and see you in August. Bye, everyone.
Thank you.
Thank you, Russell.